Hello and welcome to this clip on the mole concept and how to use it in reaction quantities. We'll start by introducing you to why we use the mole to measure amounts of substance in the first place, and a little bit of history on how the mole concept was devised in the first place. We'll then go on to look at how we use moles to work out reacting quantities in reactions once we have the balanced chemical equation. And we'll briefly introduce the equations that we use depending on what data the question gives us. So although you may well be familiar with the basic chemical makeup, or basic structure rather, of an atom, with the protons and neutrons in the nucleus and the electrons in shells or orbitals around the nucleus, it's very difficult to actually weigh atoms. They're so small, they're so tiny, their mass is almost negligible individually. So I've got to be a little bit careful not to say that the masses of individual atoms can be disregarded. That's not what I meant by negligible. Each individual atom is so small that it's very, very hard to weigh. It's almost impossible. But we need to be able to keep track of how many of them are reacting if we're going to effectively manage a reaction. So how do we do it? This is where the mole concept comes in. And what this allows us to do is measure atoms collectively. So the Italian chemist Amedeo Avogadro was able to prove that equal volumes of gas contained equal numbers of particles, irrespective of the identity of the gas. So what Avogadro did was he took pressure measurements and was able to calculate that this must mean that it doesn't matter what gas you have, it will exert the same pressure provided the volumes are identical. But because different atoms have different masses, the mass of these individual samples will differ. So looking at the examples in the bottom left-hand corner of the screen, you can see that the same volume of three different gases will have different mass. So this specific mass for each gas is called the molar mass. It's unique to every single substance, every single pure substance, and is the mass of 6.023 times 10 to the 23 particles of that substance. So particles can be taken to mean atoms, molecules, or ions. So therefore 6.023 times 10 to the power of 23 is the Avogadro constant, named after Amedeo Avogadro, and is the number of particles in 1 mole of any substance. So we can now apply this to our gas samples. So each gas sample in the bottom left-hand side of the screen contains 6.023 times 10 to the power of 23 molecules of gas. Now the way we calculate moles is dependent on the data we have at our disposal. And obviously the data that we've got depends on what measurements were taken in the first place. So ultimately, in A-level chemistry, there are 3 different types you'll come across. Now what we do in college is we teach these at slightly different points in the first term, so we're not overloading with information. So I'm going to start by taking you through moles using masses. So if you're looking at this for the very first time early on in your A-level chemistry in the first term, then it's just really moles using masses that you need in the immediate future. But by the end of the term, by about Christmas time, you'd need to be able to be confident in all 3 of these calculation methods. So I'll take you through all of them, and you can come back and revisit this clip later on in the course if you need to. So if we've got masses in grams, to work out the moles, what you do is you divide the mass in grams by the molar mass, which is grams per mole to the -1. Now your molar mass is the same as your relative atomic mass if you're talking about atoms, or your relative molecular mass if you're talking about molecules. So if you need to at this point, you might want to go and look up in your textbook's glossary the terms relative atomic mass and relative molecular mass. So now let's have a look at how we calculate moles using gas volumes. So when you're dealing with gas volumes, they can be provided either in decimeters cubed or centimeters cubed. So you'll notice that there's two slightly different equations, but they essentially say the same thing. If you've got the gas volume in decimeters cubed, you multiply the moles times 24. If you've got the gas volume in centimeters cubed, the moles are multiplied by 24,000. And that's because there's 1,000 centimeters cubed in 1 decimeter cubed. And finally, if we're calculating moles using concentrations in solutions, which will be given to you as moles per decimeter to the minus 3, the moles is calculated by multiplying the concentration in moles per decimeter to the minus 3 by the volume in decimeter cubed. Now, there's a lot of units that have come up on this screen. These are the units that must be used if you're actually doing these calculations. So it's very, very important to look at the units that you're given in the question and check, are they the same units that are on these equations in front of you and the ones you'll find in your textbook. So whether you're using this video clip or whether you're using a textbook as your point of reference, it's very important you get used to the idea of converting the units in the question that is given to you into the correct units to insert into the equation. This will happen regularly in exam questions. So it's a very important skill to be able to do this and to be able to spot when unit conversions need to be done. So let's have a look at an example using moles and masses. Now remember that moles equals mass divided by molar mass, like we said in the previous screen. I've got hold of a little animated video clip of the reaction that's up in the top left-hand corner, iron and sulfur reacting under the influence of heat in a test tube. You may well have seen this demonstrated or done it yourself prior to coming to college. So you can see that you've got 32 grams and 56 grams of reactants. So if we want to work out the moles of sulfur, we take our 32 grams of sulfur and divide it by 32.1. That 32.1 comes from the periodic table and is the molar mass, or the mass number, for sulfur. Now obviously it's going to be very close to 1. Notice I didn't round it up. So I'm just going to put a reminder in there. Don't round it, because you'll introduce error. It's incorrect to round it up. So taking 32 grams, dividing it by 32.1, that gives us 0.997 moles of sulfur. And we can do the same thing for iron. And we get 1.003 moles. So what that tells us is that we have 0.997 moles of sulfur reacting with 1.003 moles of iron. So how many moles of iron sulfide do we get? So what we do is we divide our 88 grams by the sum of 32.1 plus 55.8. So just putting that into my calculator, that gives me 87.9 grams per mole. 88 grams divided by 87.9 grams per mole to the minus 1. That's the molar mass of iron sulfide. I've added up the individual atoms. So the final calculation, 88 divided by 87.9, that gives me 1.001 moles. So I can write that in up here. So we can say that the mole ratio of iron to sulfur to iron sulfide is 1 to 1 to 1, because the masses have helped us prove it. So let's look at an example question that gets you to use this mole ratios idea. It says, what mass of potassium oxide, K2O, would you get if you burnt 7.82 grams of potassium metal, K, in oxygen? There's a little technique we can use here called DMEMA, data, moles, equation, moles, answer. Now if we look at our question, we're told that we have 7.82 grams. That's our data. So what we do is convert that to moles, which gives us 0.2 moles. So we've done the data, we've done the moles. Now the equation tells us that there's a 2 to 1 mole ratio, so therefore our 0.2 moles has to be divided by 2 to make 0.1. So we've just used the equation and we've got the second amount of moles. So that 0.1 can now be used to work out the answer. So we take the number of moles, which are 0.1, we multiply it by the molar mass of K2O, which is 94.2 grams per mole to the minus 1, and that gives us 9.42 grams, which is our answer. This technique can be applied to any mole calculation. Data, moles, equation, moles, answer. So let's now have a quick look at moles and gases. This is used if we have gas volumes given to us instead of masses. If you don't have things in grams, what do you do? So assuming we're talking about gases and they give us the volumes either in decimeters cubed or centimeters cubed, you can do V equals 24N or V equals 24,000N. And the reason for that is 1 mole of any gas, doesn't matter which, occupies 24 decimeters cubed or 24,000 centimeters cubed, as the diagram on the left-hand corner illustrates. The masses might be different, but the volumes they occupy are identical, according to the work done by Amedeo Avogadro. So suppose you get given an equation, and you're told that you have 2.3 grams of sodium, and they want you to work out what volume of hydrogen will you get if you react that sodium with sulfuric acid. So imagine that the question that's given to you is in blue. What volume of hydrogen gas would be evolved if 2.3 grams of sodium metal reacted with H2SO4? So the technique we use is data, moles, equation, moles, answer. Sometimes called Did Molly Eat My Apple, an acronym, DMEMA. So the data is my 2.3 grams. I convert that to moles using mass over molar mass. Looking at the equation, I can see that it's a 2 to 1 mole ratio between sodium and hydrogen. So if I've worked out that there's 0.1 moles of sodium made, there must be 0.05 moles of hydrogen made, because it's half the amount in moles. So that gives me the moles of the hydrogen. Then I can use my V equals 24N to work out the answer. And this can be applied to any mole calculation. It doesn't have to be moles and gases. It could be moles and masses. It could even be moles and solutions. So looking at moles and solutions, it's moles equals concentration in moles per decimeter to the minus 3 times volume in decimeters to the minus 3. Sorry, decimeters cubed. So let's apply this to a worked example. 0.552 grams of lithium metal reacts with water to form 125 centimeters cubed of a solution of lithium hydroxide, LaOH. What is the concentration of this solution? So the first thing to do is to write out an equation and then see if it balances. Now if you look at this closely, the hydrogens don't balance, do they? So you have 2 hydrogens on the left and 3 hydrogens on the right. So now you have your balanced equation. So they want us to know the concentration. So I've rearranged the equation at the top of the screen so that concentration is the subject. So my first thing to do is to work out from my data how many moles of lithium I've got. So I'm using my DMEMA technique. Now I know I've got 0.552 grams. So that's my data. I divide that by the relative atomic mass of lithium, or the molar mass as we call it, and looking on my periodic table I know that that's 6.9 grams per mole to the minus 1. So that gives me 0.08 moles of lithium metal used. So now I can use the equation to work out how many moles of lithium hydroxide would I get. And because it's 2 to 2, that's the same as 1 to 1, so you'd also expect 0.08 moles to be made for your lithium hydroxide. So we've now done data moles equation moles, we now just need the answer. So to get the concentration, the standard unit of moles per decimeter to the minus 3, you need to divide the number of moles by the volume. But the volume is given to you in centimeters cubed, not decimeters cubed. So that gives us 0.64 moles per decimeter to the minus 3 of our lithium hydroxide solution. So let's now look at a slightly more difficult exam question that requires confidence and fluidity in these skills we've looked at. So I'll talk you through it as we go. We've got to read the question to get all the information so that we know what to do with it. So it tells you that there's a multi-stage process that sulfuric acid is made using. So the first one says that 100 tons of sulfur trioxide were reacted with oxygen in stage 2. So we've got our data and we've got our equation. So because we've now identified our data and also where our equation is that we're working from, we can begin the calculation. So I'm just going to move the page down a little bit, keeping the equation in view so we can begin. So the first thing to do is to convert tons into grams, because grams is the unit we need to use for moles equals mass over mR. So if I do that calculation by putting the numbers in, I get 1560062.4. Now you'll see that I've put a little tip in. There's a maths tip. If they give you the quantities in standard form, it's always a good idea to actually answer it in standard form, because that then shows the examiner that you've got the mathematical prowess required. And that is something that they're looking out for in exam papers. So in the next one, they're asking for the mass. So although you don't have to write down the triangle in your answer, I'm popping it down in this clip just so you can see how to rearrange the formula. So it would be mass equals moles times molar mass. So because they want the number of the mass of sulfur trioxide, we've got to go back to our equation at the top of the screen. If I highlight the equation, you can see that it's a 1-to-1 mole ratio between sulfur dioxide and sulfur trioxide. So the number of moles of sulfur trioxide will be the same as the number of moles of sulfur dioxide that you just calculated, which is equal to 1.56 times 10 to the power of 6 multiplied by 80.1. So I've got to bring the page down just to complete that calculation. So that gives me 124960998.4 grams, which is converted to 124.96 tons. Don't forget again that they were talking about tons at the top, so it might be an idea to quote your answer in tons. So the next one asks us to construct a balanced equation for the formation of sulfuric acid from oleum. So although this is slightly outside the remit of this particular clip, it's not a moles question, let's run with it anyway because we're doing an exam question and they're going to throw different things at you as you go through the question anyway. So oleum is H2S2O7. So you can see that it tells you that it's diluted in water to produce sulfuric acid. So I've put my H2SO4 on the right-hand side. I've put my H2S2O7 as a liquid on the left-hand side. And I've left a little space just there in case there's something I might want to add to my oleum to make it into H2SO4. So if I draw your attention to the fact that there's 2 sulfurs in oleum and only 1 sulfur in sulfuric acid, obviously there's got to be at least 2 sulfuric acid molecules that are made from 1 molecule of oleum. This now makes the hydrogens unbalanced. So this is where the water comes in, like so. So again, we've got to move the page down a bit so we can have a look at the next part of the question. So it seems that the next part of the question is on the right-hand side of the screen. You'll see what I mean in a second. So now we're moving on to a mole calculation, but using solutions. This is moles and solutions now. Okay, so just a little bit of advice here. Always keep a lookout for what kind of units you're given in the question. So I've highlighted where all the units are. You can see clearly that we're not doing masses anymore. We're now doing concentrations in solutions. So it's a different mole calculation we have to use. It's moles equals concentration times volume that we talked about earlier. So I can collect my data, and I can convert my 25 centimetres cubed to decimeters cubed in my calculation by dividing it by 1000, which gives me 2.5 times 10 to the minus 3 moles. So the next part of the question is quite important. It says calculate the concentration in moles per decimeter to the minus 3 of the diluted sulfuric acid. So as you can see, the volume needed of diluted sulfuric acid was 20 centimetres cubed. So just read the question to make sure that you know which volume to put in here. So you have to rearrange the N equals C times V equation to make concentration the subject, not forgetting that your volume has to be converted to decimeters cubed, which will mean that the volume part of the expression is going to be 20 divided by 1000. Now to get the moles of sulfuric acid, you've got to go back to the equation. Remember, data moles, equation, moles, answer. So looking at the equation, you can see that the mole ratio is 1 to 2. So the number of moles of H2SO4 will be half the number of moles of sodium hydroxide. You've just calculated the number of moles of sodium hydroxide, so your 2.5 times 10 to the minus 3 moles has to be divided by 2. So I've popped it in a different colour so you can see, for emphasis, what I've done. So that gives us 0.0625 moles per decimeter to the minus 3. So bringing the page down, it says calculate the concentration in moles per decimeter to the minus 3 of the original sulfuric acid sent for analysis. And this is actually the end of the question. So let's go back to the beginning part of the question. And it says a sample of the sulfuric acid was analysed as follows. So I'm starting up here. And it says 10 centimetres cubed of sulfuric acid, that's your original amount, was diluted with water to make a 1 decimeter cubed solution. So we've got a volume of 10.0 centimetres cubed. So that original 10 centimetres cubed was diluted to 1 decimeter cubed with water. So the dilution factor of 100 means the original sample is 100 times more concentrated than the one you've just calculated the concentration for, which gives us 6.25 moles per decimeter to the minus 3. So now let's have a quick look at the mark scheme to see how we've done. So starting off, we've got this one, as you can see it there. And we've got 125 tonnes, or 124.96. we got the correct marks there as well. So we've got 3 so far. So if I bring the page down to have a look at the second part, I'm going to move it over like that. So we got 2.5 times 10 to the minus 3. We got, I'm going to have to move it slightly. Oops, not like that. Like this. We got 0.0625. And we multiplied that up to make 6.25 there as well. Now that's only 6 marks, and there's 7. I forgot to mention this mark here. And if you can see this bit here, we got that one as well. So that shows the examiner that we were able to divide 2.5 times 10 to the minus 3 by 2. So hopefully this has been a fairly useful introductory clip to see how you can apply the mole calculations by choosing the units, or looking at the units you're given and choosing the correct equation, and then finally applying that to a relatively difficult longer answer style question. So that although the question is structured, you need to be able to take it through the stages and follow the instructions quite carefully in order to get right to the end. If you've got any queries on this type of question, once you've practiced a few, then why not bring them into college and have a chat to one of your teachers, perhaps, or maybe come and see one of us in a subject extension. But for now, thanks for your time, and see you soon.